Morning. So, we have discussed that mechanical vibrations and their equation and equivalent electrical circuits. Now, we try to find out that wave equations, acoustics wave equations. Okay. So, now in practical, if you see when think about the loudspeaker, if the loudspeaker is play in this room, in this studio, what will happen? The sound will come from the loudspeaker to the person. So, that means the sound is traveling through the air and reaching to the person. Now, we have to know how the sound is propagated. If we do not know how the sound is propagated, then we cannot do that acoustics treatment or acoustics how the sound is propagated, how far distance it will be attenuated. All those property when we want to find out, we have to know how the sound is propagated. That means, in mathematics or if anything you know that any physical phenomena you try to model in mathematically. So, that means, I have to derive the mathematical model for that wave equations. So, as a source, when the mechanical vibration produce that vibration and that vibration has to be travel, you know that the acoustic wave does not travel, cannot travel without the medium. That means, that when a acoustic wave is travel, it use the media to travel. Now, for that purpose, if I want to how that acoustic wave is travel, if we consider how it is in your 10 plus 2, you know how the acoustic waves travel. That means, some particle of the media will move forwards and create a denser region, then it relax, then create the next particle will be. So, like that, the condensation and relaxation, that way sound wave is propagated. See that this picture of this computer, if you see this acoustic wave picture of this computer. So, this portion is denser, weaker, so that way the acoustic wave is propagated. That is why acoustic wave is called transverse wave. Transverse wave or what kind of wave? Longitudinal wave or acoustic wave is a long. So, it travels through a condensation and relaxations. So, how it travels, how it condensation is happened, how the relaxation is happens. So, we said that if the medium, you know also the one of the property that when the acoustic waves travel through a media does not change. That is that constant we put that if I consider the acoustic wave, forget about that intensity of the wave is such a large, we cannot explain that phenomena, that we are not considering. Consider the acoustic wave with regional intensity, when the acoustic wave is travels, it does not change the media. That means, if it is travel through a solid becomes solid, its property does not change. So, how that wave is travels? So, there will be some particle which condense, and due to the restoring force, particle will be restored and next particle will be, that force will be transferred to the next particle. So, that way if that acoustic wave travel, then we have to derive that acoustic wave equation. So, we are considering some constraint and then derive the simple acoustic wave equation. So, we are not deriving the acoustic wave equation which can explain the explosion of a bomb. That intensity acoustic wave equation we are not considering. We are considering when the acoustics wave travel through a media, the media does not change. So, when we derive the mathematical equation of the acoustic wave, we consider the fluid, because fluid exhibits some more constraint regarding that acoustic wave transmission. So, we derive that equation for fluid and that equation still valid for wave, air, solid and everywhere. Okay. So, simply we derive the acoustic equation for fluids. So, now if you think as a student that okay, acoustic wave is travel, what is traveling? That pressure, that if I produce a sound from the loudspeaker, the acoustic pressure which is produced by the diaphragm has to be transmitted to the listeners. That means, acoustic pressure is transmitted through the air using condensation and relaxation to the listeners. So, we have to derive that equation, what should be the equation that pressure is transmitted from the loudspeaker to the listeners. Okay. Now, instead of air, we consider let the medium is a liquid, because liquid exhibit some more constant over that. If I consider when we consider the medium property, that medium property supports by the liquids, and that acoustic wave which will be derived, still it is valid for other medium also. So, now if I consider that okay, I have a liquids, I produce a sound. Now, I said that okay, let us consider any point of that liquid, what will be there? There will be a pressure, which pressure? Total pressure, capital P, and there will be a equilibrium pressure. That means, if I not apply the acoustic pressure, external force which is acts as acoustic pressure, then this liquid has an equilibrium pressure. Let us the equilibrium pressure is capital P 0. Okay. So, what should be the acoustic pressure? Will be the small p, which is the difference between the equilibrium pressure minus difference between the total pressure or instantaneous pressure minus equilibrium pressure. So, that is the acoustic pressure. Small p is nothing but a acoustic, small p is nothing but a acoustic pressure. So, acoustic pressure is nothing but a instantaneous pressure, that means pressure exhibit in this point minus the equilibrium pressure. If the acoustic force is not applied, what should be the pressure of at that point, that is equilibrium pressure. Similarly, at that point, if it is a liquid, that is a density. Now, if I put a pressure on that any medium, what will happen? The density will be changed. Let us density will be changed. Then we consider, let us at the same point, the total means instantaneous density is rho. This is the instantaneous density. That means equilibrium density plus modified the density which is changed due to the acoustic pressure. So, density minus, what will be the minus? Equilibrium density is equal to the instantaneous density. Okay? Instantaneous density minus equilibrium density density, or you can say the density divided by the rho 0 will be the condensation, which is called S. S is nothing but a condensation. So, density of that medium is rho minus equilibrium density divided by rho 0 is the equilibrium density, is the condensation property. Then velocity. Let us how the wave is propagated. The particle will move forward, create condensation, then it will come to its rest position, again next particle will move forward, again come to its rest position. So, if the particle is moved forward, that means there is a particle velocity which creates that wave propagation. So, if the particle velocity is u, I consider the particle velocity is u, then if you see in this room, if the acoustic wave is created there, so particle velocity is free to move anywhere. It is not that it will move this direction, it can free to move. Suppose I create acoustic pressure in this point source. So, what will happen? Particle can move upward, can move downward, can move forward, can move backward, all these three directions. So, if I say that I have a three direction in this room, that means x, y and z, that means x, y and z, upward is x, y, z, x, y, x, this is x, this is y and this is z direction. So, any particle can move in this coordinate in any direction. Okay. So, u has a component that particle velocity, if the particle velocity u is nothing but a displacement of that particle with respect to time. So, particle can move any position, and if the particle is displaced, then the velocity is the displacement divided by the time. So, if the particle is displacement is psi and d psi by dt, but psi displacement can occur in any direction x, y, z. So, I can say psi is a vector which is nothing but a x with the unit vector in x direction, y with the unit vector in y direction, z with the unit vector in z direction. So, if this point is nothing but a x, y, z, so particle can move to this point which is x1, y1, z1. So, in case of velocity, displacement with respect to time. So, displacement with respect to time, and displacement is psi, which consists of 3 directions. Okay. Next is temperature. Think about in practical scenario, is when the wave is transmitted, is the temperature is changed? If it is support linear wave equation, we said this transmission is an adiabatic condition. So, that means if acoustic wave pass through a media, temperature of the media does not change. So, that means the temperature, we have constant that the temperature does not change. So, that means process is adiabatic. So, T is the temperature which is in Kelvin scale. Okay. Now, what is the velocity of the sound? If you see, the velocity of the sound is nothing but a root over of bulk modulus divided by density. Bulk modulus divided by the density of that medium. So, the velocity of the sound is root over of bulk modulus divided by the density. So, if you see the velocity of sound in air and velocity of the sound is in solid and velocity of the sound in water or liquids will be different, because the bulk modulus and density of the medium will be different. Okay. So, in that case the velocity of the air, so this is one example is given. In case of air, bulk modulus value is given, density is given. So, the speed of the sound I can derive. Similarly, in case of water, bulk modulus is given, then there is a density is given, then I can derive the velocity of the sound. Still bulk modulus is given, then the density is given, we can derive the velocity of the sound. So, if we see, you know that the solid has the highest velocity, then the liquid, then the air. Okay. Now, we want to derive that equation. Those are the preliminary part of the deriving the equation. So, we will use those nomenclature when we derive that equation. Now, if I want to derive the equation, what are the consideration? We said when sound is propagated in a medium, medium does not change, and equilibrium density of the medium in all point is same. So, that means the medium is homogeneous, isotropic and ideal fluid. Ideal fluid means there is no viscous loss, there is no friction loss, that part we consider there is no loss when the acoustics, in practical it is not, but simply we put those constant to derive that equation, then we employ one after another constant in see how the equation is modified. So, for a linear wave equation, we consider the medium is homogeneous, the process of sound transmission is adiabatic, there is no heat loss, and the fluid is ideal, that means there is no friction, no viscosity, those part is not there. So, the process is isotherm. Okay. Then we employ these 3 simple principles. One is called continuity of the mass or conservation of mass, then another is called equation of states, and another is called force equation. So, those 3 equations will be employed during the derivation of that pressure wave equation. Okay. So, our ultimate goal is to find out the pressure wave equation, how the pressure wave is travel in the medium, that mathematical equation of that pressure wave. Okay. Now, we go for one by another. So, let us equation of state. What is the equation of state? What do you know? We know pressure, total pressure is nothing but a, what is total pressure? Density into R into Tk. What is R? R is called gas constant. Density into gas constant into Tk. Tk is the temperature in Kelvin. Okay. So, pressure is nothing but a density into gas constant or specific gas constant into Tk. Now, if this is an isotherm condition, then we know total pressure divided by the equilibrium pressure is equal to rho by rho 0. Okay. So, in case of perfect gas condition or isotherm condition, perfect isotherm condition, it is nothing but a root to the power gamma. This is the in case of ideal it is rho by rho 0, but in case of isotherm condition, so this gamma is nothing but a specific heat constant. Gamma is called specific heat constant. So if this is my equation and gamma is specific heat constant, can I express this term in term of Taylor series? Can I express this in term of Taylor series? Now, if I want to express this in term of expand this term in Taylor series, then what I will get? I get P minus P is equal to total P0 plus, just express this. This is P is equal to P0 into rho by rho 0 to the power gamma. These things I express in Taylor series. So this is 1 plus first order term into difference of the density, then second order term that will come. So rho P0 plus P0 into what will come? P0 plus 1 plus, so it will be P0 plus del rho by del P by del rho into rho minus rho 0 plus second order term del P by del rho square into half of this into rho minus rho 0. That way it will got up to the all term will come square. So this is the first order, second order, then third order, fourth order, fifth order term will come. Okay. Now if I say that whole things is linear wave equation, then I consider only to the first order term. I can neglect that higher order term because I am explaining the linear wave equation. So in that case, total pressure is nothing but a P0 plus del P divided by del rho into rho minus rho 0. Rho minus rho 0. Now, if I consider that P minus P0 is equal to, I can write B into rho minus rho 0 divided by rho 0. So, what is B? B is nothing but a del P by del rho into rho 0. Del P by del rho into rho 0, because I am considering B into rho minus, so I dividing with the rho 0, so it will be multiplied by the rho 0. Okay. So, B is called bulk modulus, this is called bulk modulus, and what is rho minus rho 0 divided by rho 0 is nothing but a B into condensation S, B into S condensation. So, P minus P0, what is P minus P0? Total pressure minus equilibrium pressure is nothing but acoustic pressure, which is small p is equal to B into S. Okay. Small p is equal to B into S, bulk modulus into condensation. So, this is the one equation we have derived from the equation of state, that acoustic pressure is nothing but a equal to bulk modulus multiplied by the condensation. Okay. Now, we go for the continuity equation. What is continuity equation? What I said, that acoustic wave is propagated through a condensation and relaxation. So, in that case condensation and relaxation. So, this is a phase of acoustic wave. I consider a volume in this space like this. This is the volume in the acoustic wave propagation space. I consider a small volume, okay, which has dx, dy and dz, 3 axis, dx, dy and dz. I consider a small volume. So, if it is condensed, let us say it is condensed, what will happen? What do you mean by condensed? Some particle will enter in the volume, some particle will enter in the volume. How it is enter in the volume? Because of the particle velocity. If the wave is propagated in this direction, let's wave is propagated in x direction, what will happen? Some particle will enter into the volume, and who caused them to enter in the volume? Velocity, particle velocity. So, if this is ux, particle velocity in x direction is ux. So, what is the particle density? Density is rho. So, how many particles will enter in the volume? It depends on the density. So, density multiplied by the ux is the number of particles which enter in the volume. I have a volume, some particle enter in the volume. What will happen? The mass of the volume will be increased, but it does not support the continuity of the mass. So, that means, if some particle enter into the volume, some particles should leave out of the volume. So, that means, there is a particle velocity this direction also, this surface also. So, in that surface, if the particle velocity is rho ux and the velocity is changed due to the dx, that means, rho into ux plus new velocity is del ux by dx into dx. This way we write the change of velocity due to this dx position is nothing but a del ux dx into dx. Change of velocity within a unit distance, total distance is dx. So, change of velocity with a unit distance is del ux by dx into total distance is dx. So, we always write it is del ux by del x into dx, because dx is the distance and change of velocity due to the delta change of space, it is del ux by del x into dx. Okay, multiply by the rho. So, that much of particle will leave through the volume. Okay. So, net particle entered in this volume, entered amount minus exit amount. So, net flux of mass into this fixed volume is nothing but a rho into ux minus rho into u plus del ux by del x into dx. So, if I do that things, so this will be del ux will be cancelled. So, it is nothing but a minus del ux by del x into dx. Okay. Now, what is the mass, total mass increase of the volume? This is the density change due to the particle velocity. Sorry, there will be a del will be there, rho will be there, rho term will be there. Okay. Rho into del ux by del x into dx. So, that multiply by the total volume is the total mass change. So, I multiply the total mass increase or intake will be multiplied by the, what is the x direction, and if the x direction is dx, what is the surface area of this? It is not single pointed. So, this is the cross sectional area. So, that within the whole cross section area mass will be injected. So, this is I take one point. So, whole cross section area mass will be injected into area cross section area of that things. So, this into the cross section area, what is del y del z. The cross section of this thing is del y multiplied by the del z. So, that is the total increase of the mass. Okay. So, this amount of mass will be increases. Now, in this case it is nothing but a rho del ux by del x into dx dy dz. So, what is dx dy dz? This is nothing but a volume, because volume is nothing but a dx dy dz. So, it is nothing but a minus rho del ux by del x into del v, or I can write instead of V, I can write del V, because I take del x, del y, del z, so write del V. So, it is del V. Okay. So, that much of mass, it is negative, minus, will be increased in this volume, the total mass increase in this volume. Similarly, the wave will come from this direction, wave will come from this direction, then it will go from this direction. Similarly, wave will come from the z direction also. So, in the all 6 plane, the direction wave will come. So, in that case, generalized equation I can write, the total increase of the mass is nothing but a del u x, sorry, rho into del u x by del x plus del u y by del y plus del u z by del z into del v. This is the total. Now, what is the mass change? If the mass is changed, then what will be changed? Volume. Volume is V, del V. So, del V is the volume. So, mass change is nothing but a. So, I can write, okay. So, this I can write, what is del u x by del x, del u y by del y, del u by del u z by del z. What is the meaning of this? This is nothing but a divergence. So, it is nothing but a, I can write divergent of u is nothing but a del u x by del x plus del u y by del y plus del u z by del z. So, I can write this equation is nothing but a minus rho divergent of u into dV. So, I can write minus divergent of rho into u. U is a vector now, 3-dimensional vector u x, u y, u z into del V is the total mass increase in that volume. Okay. So, rate at which mass is increased. Now, if this amount of mass is increasing here, that is nothing but a the rate of increase of mass with respect to time, rate of increase of density. So, what will happen? If some mass is enter here, the density of this volume will be changed with respect to time. So, let us u initially it is 0. Now, once it started the mass flowing into that side, some mass will be come out, that I consider. So, net is going in minus going out is the net amount of mass increase in that volume. In that case, that increase the density of the volume with respect to time. So, I can write del rho by del t is the density change with respect to time into del v is the change of mass of that same volume. So, this is nothing but a equal to minus del of rho u into del v dv. So, dv is cancelled. So, I can write del rho by del t plus divergent of rho into u is equal to 0. Okay. In that case, what will happen? So, this is called linear continuity equation. I cannot say that if you think about, I take a ball, liquid ball, if you squeezed it, what will happen? The density of that ball will be, the volume is decreases, mass may be increases, mass has to be increases. Or if you see, I take a ball and I inject, suppose I have a fixed volume in here, air, and I put some more air in that volume with the fixed volume. What will happen? Air density will be changed with respect to the flow of the air inside that volume, means in which rate I injected the volume, in that rate will change the density of the volume. See, so, I can say the amount of mass flux which is increased in this thing will be the rate of change of density if the volume is remain constant, because I have volume, I have same, I have not changed the volume. So, if the del V I consider remain constant, that means rate of change of particle, deposited particle or amount of deposited particle will increase the density. So, in that case the rate of change of density should be equal to the net mass flux enter into the volume. So, it is nothing but this equation. So, if this is the equation, this equation is called linear continuity equation, conservation of mass. If the density, if the volume remain changed, if the volume remain changed, if more particle is entered, density will be changed. Similarly, if I change the volume, the density will be changed. So, in that case, this is a linear continuity equation. Now, if I say that okay, rho is total density, rho is the total density. So, rho is nothing but a total density, rho or instantaneous density. So, I know one is called condensation. How we say that if I apply acoustic force, some particle will be condensed in one point and then it will be relaxed, then condensed, then relaxed. So, this condensation S is nothing but a total density minus equilibrium density divided by the equilibrium density. Okay. Now, if I change this thing, this is nothing but a, so I can say rho is equal to 1 plus S into rho 0. Rho 0 S, rho is nothing but a 1 plus S into rho 0. So, rho 0 S plus rho 0 is equal to rho. So, rho is nothing but a 1 plus S into rho 0. So, if this, now if I put this thing in this equation, if I take the derivative, so del rho by del t, rho 0 is constant, so differentiation will be 0. So, del S by del t into rho 0. So, now I put this del S in here. So, what will happen in this case, that rho, this equation become del S del of S by del t, rho 0 will be multiplied instead of del rho by del t, plus what will be there, rho is nothing but a 1 plus S rho 0. So, I write divergent of 1 plus S rho 0 into u is equal to 0, equal to 0. So, now if I say if the S is very small and rho 0, I said rho 0 is constant. So, rho 0 constant with respect to time, that means rho 0 is not a function of time. So, I say rho 0 is a weaker with respect to function of time, and S is very small. If S is very small, I can ignore S here. So, in that case it is nothing but a rho 0 u is equal to 0. So, the equation is del rho by rho 0 into del S by del t plus divergence of rho 0 u is equal to 0. So, this is the continuity equation, or I can use this equation. So, sometime I use this equation, sometime I use this equation later on. Okay. So, this is called continuity equation. Okay. Next equation is the mass equation, or sorry, force equation. This is the continuity equation, mass equation. Next is the force equation. So, force equation I will discuss in the next class. Okay.